Yeah.
That's good.
Yeah, thanks. Okay, so my name is Ronan Higgins, and I was previously an instrument scientist on the grade team, and I've been working on the data since 2015. Yeah, so here's just a quick picture of grade showing with the backends on the right here, and then all the front end receiver controller here in the front, and then this, of course, telescope in the background. So the talk outline. So I kind of was how I approached this. I was just imagining being a user, getting the data from the archive, and then what does he get out of the box, and how we can move forward. So that was kind of what I was looking at. And then as Lars described, Lars did an excellent talk there, giving the background, also the analysis tools. So what I'm just going to describe is how the data reduction is going from the level 3 to the level 4 data and some of the problems you might have. The thing is, in the archive from SOFIA, from Great, there's a curated, because we have this kind of custom pipeline where, as I write here, handcrafted Gilda scripts. It should be in quotes, maybe the handcrafted, because each one had their own style, but they're all to a high standard. So a lot of the kind of the grunt work that you would do as an astronomer, hopefully we as the Great team have taken a lot of that out. And that was a big push after every flight series, that we would take the data and make these data packages that we would push into the IRSA archive then. So the hope is a lot of the things I'm showing here you mightn't see in the field, but I do take level 3 data from the archive, and then I go through, I just took an Orion bar map, and it has data problems, but I know, because I worked on the release of the level 4, that I removed all data problems, but it can be, if you're looking at other data sets, you might have some issues. And I just wanted to give people sort of the tools of how they can look at the data in class, and for a lot of people, get out of class as quick as possible. But I don't want to be dissing any class users in the community. But it is, as to support Lars's point there, the documentation is poor. It's a very quick language. You can plow through gigabytes of data. It's written in Fortran. It's got this. It's very much built for speed. But the scripting language is I don't know, vintage is maybe a better word for it. I don't know. I find it difficult to work with, like just basic things that you have in Python available in modern language you don't have in class. And it was just, it's kind of, documentation is kind of word of mouth. And as I said, there's got its pluses and advantages, and some people live by it, some people don't. So I tried to present a bit, bipartisan maybe. So I show both codes. So what I was going to get into then was just to go through the great data levels in the archive, then go through the heterodyne observations, because that's an important part of how the data is taken, how you can get bad data quality comes in. You have to understand the process of the on and off and so on. And then I just get into the great reduction process a bit, just showing the kind of, at least what I did for the larger Rhine map, the kind of the steps in the tree where you go from level 3 to level 4. And then I go through some of the instrumentation issues that we had issues with. And then I switch over to a notebook, and I go through just, how you import data, how you make averages, how you, things like that. And then export the data from class and go into AstroPy FITS tools. Yeah, so here's the kind of classic heterodyne observation routine, where you have to get your temperature scale, you observe a hot and a cold internal load at the start of your observation. Then you would observe an off, and then in this case you're looking at a mapping observation where you're doing an OTF map and you're dumping multiple spectra. And then depending on the stability of your system, your total power stability or your gain stability, you would toggle between doing hot coals or ons and offs. So typically for SOFIA, for Great, we operated with a 30-second total power stability time. That meant we took an off every 30 seconds, and then we had a hot cold every 5 minutes. So to get into the data reduction process, one of the things that I won't cover today is how we go from, so before level 3 and 4, there's levels 0, 1, and 2. I don't really cover here how we go from level 0, like raw backend counts, up to level 2. That's covered in the Great SOFIA atmospheric calibration paper, which is on the top right here. And that then includes all the atmospheric fitting, which was quite challenging, even though we were above 90% of the atmosphere, there was still, because of our high spectral resolution, we were still picking up a lot of, you could have narrow atmospheric features could fold into your line. So that was one of the things we always did pre-flight, was careful tuning of your IF band so you didn't have atmospheric features folding into your astronomical signal. And sometimes, for example, with the M51 observations, you couldn't observe it at certain times of the year because you had a large ozone line would block your C plus observation. So there was a lot going on, the atmospheric transmission, more than you would think, but I won't cover that here. So, as I said, the data was written based on heritage coming from the Cosmo and Anton telescopes. Our data was written to this Gildas class format. It's kind of it's kind of similar to FITS, but it's a sort of an internal format from the Gildas developers based out of Grenoble. So what I get into here then is I get into, how you filter the data, baseline correction, then filter the data again, and then regrading into a map. I just go through some of the issues that we had with the Orion data, for example. And so here just gives you an overview then. So GREAT had this 7-pixel arrangement. It was 2 polarizations over 7 pixels. And here I just give an overview of various types of data qualities you could have, where on the left is like what you would expect. That means you're off and you're on. We're at the same state. When you subtract the two, you're just left with the residual astronomical emission. What happens in the middle then and on the right is that during the course of your observation, your receiver has drifted. And then when you subtract your on from your off, you don't remove all the systematic effects, and you're left with this kind of large continuum drifts, worst case, but you can be left with very ratty baselines as well. And these baselines then are a product of things like the mixer coupling in the electronics, the amplification chain. So there's a good bit of physics going on there as well. You can also have the effect, so I think I get onto that in the next slide. You can also have, so this is this classic standing wave phenomenon that you have in radio astronomy, where you have internal reflections between cavities in the system, and then when you observe those in with a broadband spectrometer, you get kind of sine waves. On the left there, I show this is actually a hi-fi example, a classic example where you've got a clear sine wave, but on the right then I show an example from GREAT where it doesn't really look like a sine wave. It kind of has a sort of a wavy pattern, but it has a lot of amplitude variation, and these are kind of classic effects of standing waves that occur in the after the down conversion in the mixer. So I'm assuming you know a bit about heterodyne observations, but just a quick run through is you have a monochromatic signal locally that you beat with a broadband signal that comes from the sky. And then as one of those beat components is this down converted IF signal, intermediate frequency signal. And that's then what you can send to your backend spectrometer, which is responsive to that, in this case, 0 to 4 gigahertz signal. And there's a bit of a reference to later slides there about RFI, this radio interference, which I touch on briefly in the rest of the slides. But then, okay, the first thing on your plate is the baseline. Your baselines are ready. What do you do? So the first thing is to understand is what the physics behind it. So here I just show again this, depending on if the standing wave is coming from in front of the optics or after the optics, you get this kind of pattern if you observe the standing wave at different LO frequencies. So you have a double sideband receiver. I'm getting into it a bit too quick now, but you have a sine wave that you're folding on top of itself. And then depending on where you sample it with the LO, you end up having a sort of a beating between the upper and lower sideband. And that's if the standing wave is in front of the mixer. So if it's occurring before mixing. If it's occurring after mixing, you get no phase variation with LO frequency. And that's what I try and show here. So you see that kind of checkered pattern on the top. That means it's coming from the telescope optics, and the bottom is coming from the IF chain. The ones from the IF chain then are the ones that dominate in upgrade. So what do you do? The classic thing you would do, although saying that the modern haven't recently got data from ERAM and Apex, the data quality of the modern heterodyne receiver is excellent. So a lot of these techniques, maybe it's just for the higher frequencies telescopes, because hi-fi, which I did my PhD thesis on, also had these issues. But it seems that the higher open frequency you get, the more instabilities you're sensitive to. But as I say here, it's a typical step in the heterodyne data processing that you would flag the line, fit a polynomial, and remove the instrument effect, and then move on. But in this case, it's difficult to to do this, and Orion is actually not the best example because it's quite a narrow line, but there are other projects, for example, in 51 Galactic Center, where you have line emission over 300 kilometers, and then if you're fitting a polynomial across that, you can do, you'll start to introduce unknown effects into the data. So for this, then we had to develop an alternative approach. One of the things we did was we used, and again, based on HiFi experience, we started to generate baseline catalogs, we call them. And what we did there is we just took off measurements and we made spectra from subsequent off spectra. And then from that, then we get a measure of the response of the system without having any astronomical emission in it. And using that, then we were able to, here's an example of just multiple offs. So you can see on the H0 pixel is very stable and the V0 pixel is very unstable. You can see that huge emission. So here I'm just subtracting, the subsequent offs from each other, and you can see there's a large amount of drift in the system while the H0 behaves a lot better. So what we did then was we fitted each of those those baseline catalog spectra with a spline, and then we took that spline and used that as our sort of polynomial correction. And we scale that spline into the spectra. And here's an example then where I scale a spline that I have in a table, and then I subtract that and I take the spline that gives me the best fit. And so here on the top is the original spectra, and then on the bottom you have the corrected spectra with a very weak emission there at around here, I guess. So and this has since been applied to the Galactic Center observations as well. And this was the kind of safest way of removing baseline issues from the data and correcting it. So and this has been applied to the released Orion map then. So here just goes through the process then. It's been too much on that. And then just here is the before and after then. So on the right you have, on the left you have top left, or the top, you have an OTF scan. So you've taken the telescope and you've driven across the source and you've dumped the spectra as you went along. And then what I just plot all the spectra together on the left, with the heavy blue is the average of all, in this case, 84 dumps. And then on the right is the kind of a map. So you're looking at all 84 spectra on a map, on a waterfall chart. And then you can see this kind of typical trough here, and this kind of baseline emission you're getting in. And then once you apply the spline correction, you just get a nice smooth, although you could say there is still some residual, but in better shape than you originally gave it in. And you get this nice clean spectra out. And then that gets propagated up to level 4 then. Here's some examples then of, to go to a higher level again, to look at the map. So you take all your spectra, you scan across your source, then you get all your ungridded spectra, you grid that into a map, and you get this cube that Lars was referring to, where you've got, the orient deck and then a velocity dimension as well. And so here on the left, you can see that you have these sort of scratches, for want of a better word, on the map. And then on the right-hand side, you get, when you apply this spline correction, you get rid of a lot of those scratches and you can keep the data. Because before you would probably, if you couldn't get a decent fit, you might have actually dropped that data from the map. But then, as I said, and this is in the paper I wrote there in 2021, once we took out the first order effects, you start to see second order effects, and then away you go down the rabbit hole. But I won't get into that here. And then again, a higher level again. So you take all your tiles and you apply all that correction to it. And one of the good measures of the classic measure of your data quality is the RMS. So you just get your spectra and you just do a standard deviation or an RMS of the spectra, and then you can either plot that as a time series, or in this case I plot it as a histogram. So on the left hand side I have the H0 pixel, which we saw previously the H array behaved better than the V array. And so you can see what you want to see in those RMS plots is you want to see a very tight Gaussian with no wing on it. If you've got baseline effects, it means that the majority of your spectra are probably okay, but because your system is drifting, you start to get, your standing wave starts to ramp up, and your RMS tracks that, and you start to get these long tails come in your distribution. That's what you see here on the right then. So the blue is the original data quality, and then the V is what you get after you apply the correction. And you can see, and some tiles are better than other. And the way the map was taken was in time, it kind of went, sort of spiraled out. And up here was actually, the LO was having some issues. So you got worse and worse data quality as you got further into the Orion map, particularly towards the north. But you can see the spline correction, it doesn't 100% remove all the baseline effects, but it does tighten up the Gaussian, so you recover a lot of the baseline features. So this is just one of the things I wanted to, and I'll show an example in the notebook of, doing an RMS of the baseline. Doing a histogram of the RMS is always a useful tool, particularly if you want to differentiate between different pixel performances. You can track that nicely just doing an RMS of a bunch of spectra. So there are alternative options. So once we got our hooks into that using that off catalog, there are alternative ways you can categorize the off contamination or the baseline issues. And after we created the SkyDiff spectra, one of the things that my colleague here, Christoph Buchbinder, worked on was using principal component decomposition to use that to kind of to try and to decouple the baseline effects from the spectra, and that's been quite successful. And it's one of the caveats of the spline method is it requires a lot of computation time. You have to go through each spectra individually. While with the principal component decomposition, you can really approach whole blocks of data and just take the whole matrix and remove it, and that has a lot better performance. But with like everything, there's some caveats, and you need to be careful with how you apply the PCA method. But Christoph's working into that and is trying to make a fail-safe approach to that. But with careful choice of spectra and input spectra, you can get very, very good results from this. I just wanted to. I was hoping to do a spline fitter demo in the Great Data Reduction, but I kind of ran out of time. So there is a test. The spline fitter data is available publicly on GitHub. That was released as part of the paper, and there is a demo script here in Gildas to show you how you can do that. But if people are interested in know more, I'm happy to take questions on that as well. One of the second order effects we had, and this did affect some data in the archive, and potentially if you're looking at data that's around the IF frequencies of 1.9 gigahertz or 2.4, so depending on where they tune the line, they might have been avoiding an atmospheric feature and put your line at a 2.5 gigahertz IF. And one of the things that gave us trouble with Orion was we had radio interference. And this was at a 1.9 gigahertz, which is a known mobile phone signal. And what you get then is you get these kind of nasty, again, scratches where you just have at one channel, you will have, a 10 Kelvin absorption or, a 20 Kelvin emission over a couple of channels. And just to show you what that looks like here, again, if you look at that waterfall plot, this is just for a particular telescope, for a particular pixel. You can see this is the mainline emission here, and then you could see, the 1.9 narrow signal beating through your line emission. So all you can do here really is just scrap those channels in. It's not the end of the world. It didn't affect all channels. That was also we never got to the bottom of, but it just affected. You can see it's a 50 Kelvin emission here. It just affected certain pixels were sensitive to these effects. So just if you're around, you can check. Yeah, you can check your IF frequency. What you can do is you can just look at the channel number in class, and then from the channel number, it's 0 to 4 gigahertz. Your full bandwidth is 0 to 4 gigahertz. So then depending on where your channel is, you'll be able to extract the IF frequency. Like Bluetooth is way worse than Bluetooth would apps because it's got this channel hopping mode, and it happened a few times that people forgot to put on their headphones, laptop, phone on the aircraft, and then the Bluetooth would it just really bakes in because it has this channel hopping, so you'd end up having 3 or 4 70 Kelvin lines baked into your and it looks a lot more astronomical than the narrow band GSM frequency. So if you're looking for lost emission, look around 2.4 gigahertz. You might find something there. Just going to hear how radio interference gets up. We know that we're observing at, in this case, this is the O1 line, 4.7 terahertz to 1.9 terahertz. The IF signal gets in, the RFI signal is from between 0 and 4 gigahertz, that gets in the down conversion part of the signal chain. So not much you can do about it. Okay, so getting out of let's get on to some of the more interesting things then, and kind of come back to what Lars was talking about again. Here's a feedback example. I just wanted to walk through, if you go to the archive now and you can download that link directly, this is what you'll get inside it. And here's a very nice map produced by Robert Simon. And this is like, all the things I discussed previously, you wouldn't have to worry about those here. So you can see the map looks pretty decent. You can immediately do science with this. So what's in the file then? So what you have here then is you've got numerous PDFs. One is the in-flight log. So that's like what we typed on the flight. This happened, that happened. That can be useful sometimes if you have some issues with your data and you want to see what happened exactly on the flight. Was there an increase in altitude, or did something happen? Was there clouds? It can be useful to read that. Then there's a kind of a formal document that describes what main beam temperatures were applied, and some details in the data reduction. So that's 2 PDFs, and then there's a project overview which just goes through which flights are in this data package, which scan numbers, and and these are all things that aren't. And one of the things I'll get onto later is because the class data structure is so rigid. There's a lot of data not in there like that. So when we write the first iteration from our calibrate program out, we have a lot of header information. But as soon as you export that data again in class, all that additional header information, like the mission, the observer name, the mission ID, there's a couple of ancillary information that can be useful there. For example, the plan ID, especially for us that are doing bulk reduction, and it's one of the reasons. One of the kind of drawbacks of class is that the data format is very, very restrictive. And then there's the data itself then, and class reduction script. So here we have, we've got 2 files there. There's the TA star scale and there's the T main beam. So in this case, and again, I'm assuming a bit what I'm talking about here, and Lars already touched on these different intensity scales you have, but the two scales we supported with GREAT were the T main beam antenna temperature and the TA star antenna temperature. T main beam is just you've scaled the data to just include the intensity in the main lobe, and then the factors for that then are stored in the class file, which will also include then the steps to go from this here to this here. So this is kind of the details, and then depending on who's reducing it, there was maybe 7 or 8 of us worked in total on reducing data. Everyone has their own different flavors of class scripts, but they all produce more or less the same quality because they went through the quality control of the PI, Yerbyshevsky and Ralph Houston. Okay, so I'll try a live demo, and this is going to be, it's just a ball of code, but I'll walk through some of the things in it. So one of the tools I use, one of the things that Lars was touching on there, is that spectral cube. That's a very useful library. But there are other things, I'll mention them as I go through. But there's also of course, AstroPi and their FITS tools are core of this. And here I just have everything that I'm importing. But the ones that stand out are, I use Pandas a good bit to handle the FITS tables that I'll talk about later. And then we use the units library in AstroPi a lot, and also the FITS that everyone's familiar with. And then there's a couple of helpers for the notebook to display images and so on. One of the things.
Lars, you suddenly muted yourself. Sorry, not Lars. Ronan.
I don't know, but what you can do is you can quickly make a class kind of a template script and then substitute variables into it that can be difficult to program in class. And I can show some examples in how this works, but this is kind of a helper class where you pass in basically a string that's the entire class script, and then this gets run in the background just using the subprocess calls for class. So it runs, anyone's familiar with the class no window, runs in the background, pipes all the logs to a temp file, and then displays that log afterwards. I'll just show you how that works in later files. But the first step is getting data into your notebook. So this notebook, as well as sharing it on the school webpage, and also this is also on Git, and it's built out from a talk actually one Verbena gave last year to the same school, where we use a notebook to just run through some analysis. So yeah, as to go back to the original point, the first step is getting the data from the archive. One of the really nice things about the IRSA archive is that you can just wget data straight from the archive. So if you search for data and you look for your AOR string and you find the data you want, if you scroll over, in this case I'm on the Great tab. If you scroll over on the table, you can just get the straight URL link to it, and that you can just wget to your directly to your terminal, and then you can start tar it and play around with it. So I was playing around with a few there. I won't run this now, so it'll probably blow up my face, but I made this helper script that'll, save it to a local folder if it's there. If it's there, it doesn't do anything. If it does, it'll save it, untar it, and track it, and untar it. Yeah, so here's a couple of details in. So here's the first footsteps into class scripting then. So one of the core commands in class is that you do a file in. So this is, if you get class up in the terminal, see that if you load up class, if you've installed it correctly, which can be a journey in itself, you get here, and then here you can do things like file in. This actually works. And basically what I'm doing here then is I'm doing these commands through the Python notebook, and I'm not doing it through the class command line or scripting, because that's kind of cumbersome. So what I do here, I'll just do these one commands just so you get an idea what I do. But so I did that. So I put a file in, and then I do find, and then it tells me, okay, there's whatever I found. It has this index system where it's got sort of a small overview of the data in an index. So if you type find, it'll show you what's in the index currently. And then what you can do is you can do list. You just list everything that's in the index, which comes out in this table format. Or a useful feature is this list TOC, and this kind of is the table of contents. As Lara said, there's good help. Like the documentation for these core functionalities is very good. But once you get to the more, the more technical things like making plots, for example, I don't know how to make a plot in I don't know how to make a custom plot in Greg in class. It uses Greg software. Things like that I find difficult to do. But for this quick view of the data, you can use this command line tools. But as I said, I won't go back to this again. I'll just do it the whole way now in Python. So what I have here, I just have this file in, and then already you start to see the advantages of the Python approach, because now instead of having to change or pass the file name in as an argument in class, I can do this, with Python variables, where I just use the nice string tools in Python, where I can substitute in environment variables or dictionaries directly into strings. So I think I'll feel safe enough to run this one. Yeah, so that guy then ran in the background the class script, and then outputted the output to the file. Okay, so then inside the file, what do you have? You have the source name we gave that during the flight. So this is OMC Center, and that was like just a sort of a local name we gave during the observations. But then in addition, you have a lot of ancillary products that may or may not be useful, like the cal, sig and cal image are very internal, deep in the calibration code that we use for debugging. But then you have things like the atmospheric emission in the image and signal band. You've got the average. Then you've got the spectra we fitted the atmospheric data to, which is sometimes important if you're worried that your atmospheric fit isn't holding up. And then there's this thing that I mentioned previously, the sky diff. And then there's a hot cold, which is a kind of a spectra you make. That's a calibration product. I give a small breakdown here of it. This being the when I check it in. Yeah. So then let's get into more detail. Then let's start looking at. Let's look at what's inside those spectra. Let's pull up a few spectra and see what we get. So then this is getting into heavy class. So what I do here is I to loop over, I won't get into too much details here, but I basically load in the file and then I make a spectra per pixel. So I get the pixel names, I load that into a structure, and then I loop over each of them and just average them together. And that's kind of what I'm doing here. I'm loading the telescope names into the telescope variable, then I'm looping over each telescope, and then I'm averaging, I do a find, which will just give me that telescope, then I average those down, and then I just plot that, and then I move on, and then I write it out just to the file. And then I have these variables that I can pass in from Python. So limits, how much I want to smooth. So here you can see the Y limits, smooth box, I just do 2 channels. And then I just pass that whole dictionary, all the local variables in. It's not the cleanest Python code. And then I just run that. And then the nice thing is this is how you make a plot in class. So then I get a plot at the end, then showing me, in this case, this is the T-rec. So I have this source T-rec. I do set source up here, and that'll just give me only the T-rec part of this and nothing else. And then I just plot those and average them. So on the left, you have the average per pixel. And then on the right, you just have, all the spectra for all pixels. And the left kind of gives you sort of an idea of the average response. And then the right will give you a sort of what the kind of time, a rough idea of the time response, if the T-rec was stable or if the T-rec wasn't. And this on the right there is a decent enough example. You can see the T-rec was pretty stable throughout the observation. Then T-sys then has the atmospheric contribution folded in. You can see it starts to get just a bit more scatter here. Then there's the tau signal. Again, it's with the average per pixel over that entire flight, and then the individual spectra. And then I plotted up the sky minus obs. So this is a spectra that we make where we subtract the off emission from, or we subtract the hot from the off emission, and then that gives us a spectra which we fit with an atmospheric model, and that gives us from that we can determine the level of water vapor in the atmosphere and use that then to generate the tau. So can be useful to look at. There's an additional spectra called sky minus obs fit, and that will show you the fitted spectra. What's interesting here is you can see these atmospheric lines here. Here's an obvious large one, but you can see around where our line emission is, it's free of atmospheric emission, which is something you might want to check. If you had something fishy going on in your emission region, you might check the sky minus hot obs or fit. Can you pull up the fit? Take a chance. Okay, so I shouldn't try any more cells after this. So here's so just one point is have a look at the sky minus obs if you think there's something fishy in your line emission, because it could be an atmospheric line that isn't. If your system is drifting, the atmospheric line will be stable during the observation, but its continuum level or gain could change, and then you end up it doesn't subtract out cleanly. And I've seen that in some examples, particularly with the large lines. If you have some gain variation, you might end up having that in your atmospheric line. Then there's the sky diff I talked about. This. I just subtract subsequent offs from each other, and here's where the spectra are really ratty then, because you're deliberately looking at spectra that are far away in time, and you get these wobbly baselines here. Okay, I haven't talked too much about astronomical data yet, but then here's an example, and again I won't get into the details, but I'm doing that trick again where I'm getting the list of telescopes, then I'm looping over the telescopes, averaging them together, and I'm looking now at the astronomical signal. And then here you go. So what I did first here, I did this command called go where, and that shows me the actual positions on the sky. So in this case, we just did a vertical scan across the source. I think normally there was a vertical and a horizontal. I think this tile was split over two flights, so we just did maybe the horizontal on the last leg and the vertical on the first leg. And then you can kind of see here already the data quality isn't that great. There's a lot of I haven't done any baseline coverage here. I've just averaged them all together, and you can see there's a lot of wobbliness going on here. But again, as I showed in the presentation, you can clean up a lot of this with the baselining tools, and this has already been done in the level 4. So if you pull the completed Orion map is in there, and all these features have been removed. But just if you're looking at other data, these issues might be there, and you should do these kind of sanity checks in advance before you get into it. I didn't touch the level 4 data here. yeah, I should have really pulled up a data cube, but I haven't done that here. What I wanted to get into was the data cube. So what do you do? So what I did do here is I made a data cube by hand, so using the class. So I took that level 3 data, didn't do that much correction on it, and just made a map on it just to show how you make a map in class. And this is, again, this is one of the things that class is, it's bread and butter. So this is pretty straightforward and very quick when you compare it to comparable tools in Python, at least comparable. So what you have here is you load in your spectra. So this is your ungridded spectral file, and then you set your mapping parameters. In this case, I read it in and I do a rough baseline, and I resample it to a certain resolution I want. And I set a window so the baselining ignores a certain line region. And then once I have that kind of cleaned, but like with just polynomial base 3, I put that into the map maker. And then all that is just basically these 6 lines here where you kind of push it into a structure or table. Then you set the beam size and the pixel size you want to get out. And then you just say XY map makes the cube. And then what I do here at the end, I just export that cube. So you get this thing called an LMV cube. And I export that to a FITS cube that I can use then tools like as Lars talked about, I can use tools like Spectral Cube to plot that data. So one of the nice things about having this in Python then is I can also now, as I described earlier, I can drop parameters into the class script. Again, an experienced class user would be able to do this within the class environment, but for me, it was just easier to do like this, where I can drop in parameter names and values into the class script, run it, and then I can run through like multiple variations of maps. Then, for example, here I've just done the V map, but I could also do like, just do the H on its own, just do the V array on its own, or do both, and then you kind of get a feel for where the damage has been done on the spectra. So I guess if I did H would probably be in better shape than V, so it might be the best example to show. So okay, I've made my cube then, and I've exported it to FITS, and then I want to look at it, and then I just did this rough spectral cube, and again the data isn't in good shape. It's not the best advertisement for great, but I've already shown some of the good data quality, so I think you can trust me that with a bit of work you can get this out. And as I said, a lot of the level 4 data is already in good shape, so you probably don't have to do this, but just if you are in the woods a bit, you can rely on these scripts to maybe get you out. But you can also potentially use the class scripts that are in the data releases, because they have a lot of tricks and details about how you can reduce the data to better quality. But here I use Spectral Cube then to just make an integrated intensity map. And they have these really nice features where you load the cube in. So here's me I read the cube in here, cube dot, where do I do it? I read the cube in here, Spectral Cube, and that's the FITS file name that's generated by Gildas. And then I just take a limit over a certain, between -5 and 15 kilometers per second, and then I do a moment order 0 on that, and then I have an image I can just show with the regular matplotlib tools, and then I get that out. Yeah, not the greatest map, but it just gives you an idea of the kind of how the process would work. And it's good we shouldn't always show the shiny data. It's good to show people that, it isn't all smelling the roses. Yeah, there's other things you can do then with the cube. You can also do means over certain axes. You can also do very nice, just a region with the spectral cube. I haven't shown that here, but there's ways you can just say, give me, the Orion Bar region, average that together, and you can do all that very quickly with this these spectral cube tools. Yeah. So as I've shown now, we've kind of moved out of class and we're into Python, where we can do other things. One of the things you can also do is, instead of just working on the cube, you can also work on the like if you get a map from the archive and you really weren't happy with the data quality and you wanted to redo that, there are ways you can go from level 3 to level 4 outside of class, where you can use tools like SciGrid, for example, which I give a small demo at the end, where you can use that as a Python tool developed in Effelsberg and used by GPT, for example, to generate maps. That's a very reliable tool as well. So what I show here then is how you can take the class spectra and export that to a FITS table. And this gives you a lot of useful tools and that are difficult to program on your own in class. So here I go. I export the data. I won't get into details, I'm running out of time. And then I have this lot of tools here, but this is kind of a function where I give that fits table to this function, and it will generate additional columns, which I call just stats or integrated intensity of like RMS, mean, median, and I can do things like track the integrated intensity. And this is things I can't do in class because I can't add additional columns to the class spectra. But in the fits table, I can add as many columns as I want until I run out of memory. So here I run through it, and then what I can do then is I can do nice things like bring it into a pandas table. Hopefully people are familiar with pandas. It's kind of a local database tool, very popular in Python, but you can do a lot of interesting like group by and cropping of data, and you can do a lot of statistics directly on it. And here's an example then. Like it would be difficult, and I know the likes of Robert Simon here in University of Cologne would be able to do this in Gildas, but for me it would be beyond my Greg abilities to make a histogram in class. So you can do this very easily then in pandas with the addition that you have a load of online support, and then you can do things like break it out into a grid. Here you have these tails. Then you kind of get a feeling for which pixels potentially behaving, but these seem to have a sort of universal performance. That's all right. What's interesting here is you can also do a timeline then, and timeline tools aren't that great in class, but what you see here is the data was obviously taken over 2 flights, I think, and what you see is on one flight, which is over here, you can see there's a large scatter in the RMS, and then on the second flight you have this kind of it narrows down. So there's obviously an additional layer there that we could look as the instrument scientist. You could look into that. Just to wrap up, I won't get into this, but you can also use SciGrid then to do this. There's demos available online where you can make a map also in SciGrid after the fact. Okay, I'm almost out of time there. So I just wanted to wrap up. Just to reiterate that point, the release data in the archive is of good quality. Like the instrument team, as we went through that data, the only problem is that it's not part of a pipeline. So there's different people have different approaches to doing it, but the universal product, the output product was of good quality. Yeah, use the class scripts inside the release packets to inform yourself of the reduction steps. But I would recommend, you're not a class expert, move to fits as early as possible. As I said as I showed in the notebook, there's a lot of like CAS that supports that SD fits format. The GPT have a lot of tools that use SciGrid. You can use SciGrid directly. You can use pandas. You have a whole plethora of options. And as Lars mentioned, there's once you get into the analysis, and you've got the dendrogram and all that sort of things available in Python as well. For people who are building instruments, and that's what we're doing right now in Cologne again with the CCAT telescope. We're building a Heterodyne system. We won't use Gildas for our data format going forward because we need the additional metadata. So what we had for Great is we had a parallel housekeeping database, and ideally you want to keep all that data together with your data format. So if you're debugging instrument problems, you can do that on the data directly and not have to go to external systems. And already now those two data sources are drifting apart, and we've no way of putting them back together. So for CCAT, we would start to either write directly in SDFits, which we've implemented already, but we haven't really advertised, or we move to some even more modern format. Maybe HDF5 or Parquet is also becoming popular. So that was it. Just to sort of, I don't know, hope that was useful. But if you have any questions, feel free to ask.
Oh, we do have a question in the chat.
Yes. This is going back to the data quality, but I was just referring to you're flagging out RFI regions in your fits. Are you basically giving up on getting any scientific information from that region?
Yeah, if you looked at the raw data, you can see there. You basically give up on it, Laura. Yeah, because and that was one other reason it was in. It was actually difficult to do that in class because you had to track those channels, and there is some support for that in class. But long story short, you basically give up on that region. Yeah. Okay. It was narrow if it wasn't Bluetooth, but it was narrow, so you just had to take the hit. Yeah.
Okay, thank you. Are there any other last-minute questions before we go for our break? Also, if you think of questions later, we can have them at the end as well. Okay, there is one. So it said, I wish we had more time for reducing data with class. I was wondering if it is possible to share the link to the Jupyter notebook that you demonstrated.
Absolutely, yeah. This will we'll put it on the SOFIA, but it's also kind of a living document. We have a GitHub where we keep it updated. So I hope it's useful. You have to have class installed on your system, and it's very Ubuntu directed. So yeah.
So can you add the GitHub link as well to your presentation later?
Yeah, it's in the presentation.
Okay, good.
So,
Thanks. Thank you.